Hello, we are from Group 10 and in this video we are going to discuss about magnesium tandem alloy. What is alloy? An alloy is a combination of metals and of a metal or another element. Alloys are defined by a metallic bonding character. An alloy may be a solid solution of metal elements, a single phase, or a mixture of metallic phases, two or more solutions. Intermetallic compounds are alloys with a defined stoichiometry and crystal structure. Alloys are used in a wide variety of applications. In some cases, a combination of metals may reduce the overall cost of the material while preserving important properties. In other cases, the combination of metals imparts synergistic properties to the constituent metal elements such as corrosion resistance or mechanical strength. Here are the examples of alloys: solder, steel, brass, pewter, duralumin, and bronze. Next, what is magnesium? Magnesium alloys are mixtures of magnesium with other metals called an alloy, often aluminum, zinc, manganese, silicon, copper, rare earths, and zirconium. Magnesium is a lighter structural metal. Magnesium alloys have a hexagonal lattice structure, which affects the fundamental properties of these alloys. Plastic deformation of the hexagonal lattice is more complicated than in cubic latticed metals like aluminum, copper, and steel. Therefore, magnesium alloys are typically used as cast alloys. Cast magnesium alloys are used for many components of modern automobiles, have been used in some high-performance vehicles. Die-cast magnesium is also used for camera bodies and components in lenses. Most common use in flares and pyrotechnics, including incendiary bombs. It is lighter than aluminum and is used in alloys used for aircraft, car engine, casings, and missile construction. The hydroxide made of magnesia, chloride, sulfate, Epsom salts, and the citrate are used in medicine. This is the physical properties for magnesium alloy. And here are the chemical properties and the mechanical properties of magnesium alloy. The application areas of magnesium: leather, engine block, luggage, chainsaw, bicycle, laptop. What is tandem? Tandem or tin is a silvery white metal that characteristically has a faint yellow hue due to slight oxidation. Tin, like indium, is soft enough to be cut with much force. When a bar of tin is bent, the so-called tin cry can be heard as a result of sliding tin crystals reforming. This trait is shared by indium, cadmium, and frozen mercury. Pure tin after solidifying keeps a mirror-like appearance similar to most tin alloys such as in pewter. The metal solidifies with a dull gray color. Tin is a post-transition metal in group 14 of the periodic table of elements. Tin is a soft, silvery white metal with a bluish tinge, known to be the ancients in bronze, and alloy with copper. It is widely used for plating steel cans used as food containers, in metals used for bearings, and in solder. Tin is non-toxic, ductile, malleable, and adapted to all kinds of cold working such as rolling, spinning, and extrusion. Here's the list of physical properties of tandem. And here are the chemical properties and mechanical properties of tandem. And here are the application areas of tin. are thin plate foil, collapsible tube, solder, tin powder, coating steel cans. And now I'm going to explain to you what is magnesium standard alloy. Magnesium alloys are widely used in automobiles due to their advantages such as low density, high strength-to-weight ratio, high specific toughness, and environmentally friendly. The established trend in weight reduction of magnesium alloys would also find a way to powertrain applications. For some critical industrial applications, such as transmission housings and crankcases, elevated temperature 150 degrees and above, mechanical properties and creep resistance of alloys are of paramount consideration for researchers. It is reported AZ91 alloy delivers poor high-temperature properties. The major reason for poor crit strength of AZ91 alloys is microstructural degradation that takes place at elevated temperature. As far as AZ91 alloy is concerned, the principal room temperature strengthening element is Mg17 aluminum 12 intermetallic. By virtue of low melting point of this intermetallic, which is 437 degrees Celsius, and higher diffusivity in magnesium matrix, these coarses at a faster rate and unstable at higher temperature above 120 degrees Celsius and no longer act as a barrier for dislocations movement. 2, 4, 5. Further, Mg17 Al12 has a cubic crystal structure due to which it is incoherent with the HCP magnesium matrix. The presence of this phase leads to poor elevated temperature properties. Therefore, it is imperative to develop high-temperature magnesium alloys for possible application in hot components. Among the magnesium-based alloys, magnesium standard-based alloys have attracted a considerable interest for their potential application at elevated temperatures. The intermetallic magnesium 2 stannum phase has a higher melting point, which is 770 degrees Celsius than that of the magnesium 17 aluminum 12 phase magnesium 2 stannum. The magnesium 8% alloy contains magnesium 2 stannum intermetallic phase and magnesium 8% stannum 3% aluminum 1% alloy contains both magnesium 2 stannum and magnesium 2 silicon, where the melting point is 1102 degrees Celsius intermetallic phases. Magnesium standard-based alloys are therefore likely to be creep resistant at elevated temperatures than magnesium aluminum-based alloys. Researchers have studied the compressive creep behavior of magnesium standard alloys. In this case, an attempt has been made to investigate the magnesium standard alloy.
There are four types of isothermal reaction for phase diagram, which are eutectic, eutectoid, peritectic, and peritectoid. The example of isothermal reaction that we can get from phase diagram of magnesium stannum is eutectic reaction. For example, liquid undergoes eutectic reaction at 560 degrees at the composition of 63 weight percent magnesium and 37 weight percent of stannum to produce alpha plus Mg2Sn. For another example is liquid undergoes eutectic reaction at 200 degrees with the composition of 2 weight percent of magnesium and 98 weight percent of stannum to produce Mg2Sn plus beta Sn. Intermetallic compound is a complex structure in which solute atoms are present among solvents in certain specific proportions, which contains two or more metallic elements to produce a new phase with its own composition, crystal structure, and properties. It almost always very hard and brittle. intermetallic compounds similar to ceramic materials in terms of their mechanical properties. It often dispersion strengthened alloys contain an intermetallic compound as the dispersed phase. For example, Mg2Sn. For phase diagram of magnesium stannum, the red line indicates the intermetallic compound, which is Mg2Sn, which you can see it here. Solid solution is formed as a result of adding of impurity atoms to a metal. Solid solution is an alloy in which an element is dissolved in one another to form a single phase structure without changing the crystal structure, and no new structures are formed. Solid solution is made of two parts, which are solvent and solute. Solute is minor part of the solution, which is dissolved impurity. Dissolved element or solute atoms an element or compound present in minor concentration. It can be either metallic or non-metallic. For solvent, it is a major part which dissolves the solute. Solvent is base element or host atoms, element or compound present in a greatest amount, and it is metallic. There are two types of solid solution, which are substitutional solid solution and interstitial solid solution. Solute or impurity atoms replace or substitute the solvent atoms for substitutional solid solution. Solute atom can substitute in the crystal lattice, and the crystal lattice of the parent element or solvent is unchanged, but it may be distorted. For interstitial solid solution, solid or impurity atoms fills the voids or vacant spaces among the solvent atoms. Solid atoms fit into the space, for example, void. It's also called interstice, and between the solvent or parent atom, it can form when one atom is much larger than another. Atoms that can form interstitial solid solution due to their small size are hydrogen, carbon, nitrogen, and oxygen. This is microstructure of solidification process. For hypoelectric, T1, alloy in fully liquid. T2, solidification process of nucleus alpha started at temperature Ts. T3, percentage of solidification process of nucleus alpha increase. T4, the last liquid undergoes eutectic transformation, where it changes to become solid eutectic, lamella alpha and beta. For hypereutectic, T1, alloy in fully liquid. T2, solidification process of nucleus beta started at temperature Ts. T3, percentage of solidification process of nucleus beta increase. T4, the last liquid undergoes eutectic transformation, where it changes to become solid eutectic, lamella alpha and beta. For eutectic, at temperature eutectic Te, alloy undergoes process of eutectic transformation, as you can see in the figure below. At point A, the temperature is 870 and its composition is 55% stannum and its phase is liquid. At point B, the temperature is 670 degrees. At point C, the temperature is 620 degrees. At point D, 400 degrees. For point BCD, the composition is 45% magnesium and 55% stannum. For point B and C, the phase is liquid plus Mg2Sn, but for point D, the phase is alpha plus Mg2Sn. For point E, the temperature is 870 degrees. Its composition is 70 weight percent stannum and its phase is liquid. At point F, the temperature is 770.5 degree. At point G, 790 degree. At point H, 240.5. The composition for FGH is 30 weight percent magnesium and 70 weight percent stannum. For point F and G, the phase is liquid plus Mg2Sn, but for H, the phase for point H is alpha plus Mg2Sn. At point I, the temperature is 820.5 degrees Celsius. Its composition is 80 weight percent stannum and its phase is liquid. At point J, the temperature is 700. At point K, the temperature is 410.5 degrees Celsius. And at point L, 180 degrees Celsius. For point JKL, the composition is 20 weight percent magnesium and 80 weight percent stannum. For point J and K, the phase is liquid plus beta Sn. For point L, the phase is Mg2Sn plus beta Sn. At point M, the temperature is 850.5 degrees Celsius. The composition for point M is 90 weight percent stannum and its phase is liquid. For point N, the temperature is 470 degrees Celsius. At point O, 300 degrees Celsius. At point P, 170 degrees Celsius. The composition for point N, O, and P is 10 weight percent magnesium and 90 weight percent stannum. For point N and O, their phase is liquid plus beta Sn, and at point P, its phase is Mg2Sn plus beta Sn. For point Q, the temperature is 660 degrees Celsius. Its composition is 98 weight percent of stannum and its phase is liquid. For point R, the temperature is 150 degrees Celsius. Its composition is 2 weight percent of magnesium and 98 weight percent of stannum, and its phase is Mg2Sn plus beta Sn.
Now I am going to discuss about the details of each microstructure with different weight percent of tin. First, at point A, B, C, and D are located at the line of 2 weight percent of tin. At point A, the microstructure is in liquid phase at 800 degrees Celsius and with composition of liquid equals to 2 weight percent of tin. At point B, the microstructure is in alpha plus liquid phase at 645 degrees Celsius and with composition of alpha equals to 1.5 weight percent of tin and composition of liquid equals to 5 weight percent of tin. At point C, the microstructure is in alpha phase at 450 degrees Celsius and with composition of 2 weight% of tin. At point D, the microstructure is in alpha plus magnesium tin alloy phase. At temperature of 200 degrees Celsius and with composition of alpha equals to 0.5 weight% of tin and composition of magnesium tin equals to 71 weight% of tin. Point E, F, and G and H are in at the composition of 8% of tin. At point E, the microstructure is in liquid phase with at 750 degrees Celsius and liquid composition of 8% of tin. At point F, the microstructure is in alpha plus liquid state at 620 degrees Celsius and alpha composition is 5% of tin and liquid composition is 15.5% of tin. At point G, the microstructure is in alpha phase with temperature of 500 degrees Celsius and with composition of alpha equals to 8% of tin. At point H, the microstructure is in alpha plus magnesium tin phase and at temperature 300 degrees Celsius and with alpha composition of 1.5 weight% of tin and composition of magnesium tin equals to 71 weight% of tin. Point I, J, and K are in the line of 25 weight% of tin. At point I, the microstructure is in liquid phase with at 700 degrees Celsius and with composition of liquid equals to 25 weight% of tin. At point J, the microstructure is in alpha plus liquid phase and with temperature of 580 degrees Celsius and alpha composition is 13 weight% of tin and liquid composition is 32.5 weight% of tin. At point K, the microstructure is alpha plus magnesium tin phase and with temperature of 340 degrees Celsius and the composition of alpha is 2.5 weight% of tin and composition of magnesium tin is 71 weight percent of tin. The point L, M, and N is in the line of 37 weight percent of tin. At the point L, the microstructure is in liquid phase at temperature 800 degrees Celsius with liquid composition is 36.9 weight percent of tin. At point M, the microstructure is at phase alpha plus magnesium tin phase and at 562.1 degrees Celsius, and alpha composition is 14.48 weight percent of tin, and magnesium tin composition is 71 weight percent of tin. At point N, the microstructure is alpha plus magnesium tin phase so same as at point M. At temperature 390 degrees Celsius and composition of alpha equals to 4.5 weight percent of tin, and composition of magnesium tin is 71 weight percent of tin. Lastly, the point O, P, and Q are in the line of 45 weight percent of tin. At point O, the microstructure is in liquid phase at 710 degrees Celsius with composition of liquid is 45 weight percent of tin. At point P, the microstructure is in liquid plus magnesium tin phase and the temperature is 590 degrees Celsius, and liquid composition equals to 40.5 weight percent of tin, and magnesium tin composition equals to 71% of tin. At point Q, the microstructure is in alpha plus magnesium tin phase at temperature of 330 degrees Celsius, and alpha composition equals to 2.5 weight percent of tin, and magnesium tin composition equals to 70.71 weight percent of tin.
Method to improve material properties for magnesium and tins alloy, which is process equal channel angular extrusions to improve wear behavior and microstructure of magnesium tin alloy. Let me explain details about this method. This method investigating the wear behavior of magnesium 5% tin alloys, focusing on the alloy process by equal channel angular extrusions (ECAE). ECAE, which is equal channel angular extrusion, is a technology used to refine grain size and therefore improve the mechanical properties of metals and alloy. The influence of the ECAE process on the wear properties of magnesium tin alloys and the wear mechanism of this alloy during sliding were explored. The relation between the microstructure of the alloy of the ECAE and the mechanical properties of the alloys was examined. In this process, it will investigate the process ECAE microstructure of magnesium and tin alloy by scanning electron microscope and X-ray diffraction. These two methods used in order to improve wear behavior and microstructure of magnesium tin alloy. These two processes each refine the grain size of the magnesium tin alloy. The hardness of the alloy also improved, and the relationship for these two is the wear resistance improvement is caused by the grain size refinement. Based on this experiment, there is a procedure to use this method, which is equal channel angular extrusion. Firstly, the magnesium 5% tin alloy was produced using ingot casting method. Secondly, the pure magnesium and the pure tin were placed in stainless steel crucible and melted in protective gas, which is SF6. After that, these two pure magnesium and pure tin were superheated to 800 degrees, and then at 720 degrees it will pour into a die steel mold. There is a specific dimension for this mold that I'm not mentioned, and I will put at the reference. Fourth step, ECAE process. As cast, already cast, magnesium and tin alloy specimen were machined into billet via electrical discharge machining and then heated in the die for 20 minutes before extrusion process. Next, the specimens were extruded in a sharp 120 angle, which the die for this method ECAE was preheated to 300 degrees Celsius. Next, the extrusion rate into the specimen is 0.022 millimeter per second, and the specimen were quenched in air after the ECAE process. Seventh step, which the specimen for the wear test were machined into cylindrical pins via wire electrical discharge machining. After that, the microstructure of the S-cast and ECAE process magnesium tin alloy specimen were investigated by scanning electron microscope and X-ray diffraction. This is two method used in ECAE I already explained before. The hardness and wear behavior were measured using vigorous hardness test and dry sliding wear test. And lastly, the surface of the worn specimen and the wear debris were observed by SAM and XRD to clarify the wear mechanism. There are some examples of engineering industrials application use for magnesium and tin alloy. For example, portable electronic device. It is widely used in our daily use, like our laptop, our smartphone, remote control, and another mobile device. And also for automobile use in industrial. case. Okay, thank you.
Materials preparation and microstructure characterization. An alloy with a nominal composition of magnesium tin in weight percent was prepared in an electric furnace under protective atmospheres of carbon dioxide and sulfur hexafluoride. The homogenization of the cast alloy was carried out through a multi-step heating process. Firstly, hold at 300 degrees Celsius for 4 hours, then 420 degrees Celsius for 24 hours, and finally solution treated at 460 degrees Celsius for 2 hours, followed by quenching into water. The aging treatment was then performed in the drying oven at 200 degrees Celsius for various holding times. Phase constituent analysis was carried out in a Brooker DW100 X-ray diffraction machine. Transmission electron microscopy specimens were prepared by twin jet electro polishing in a solution containing 3 ml of perchloric acid and 297 ml of ethanol. This is Figure 1. Figure 1 shows the effect of alloying additions in solid solution on A and C lattice parameters of magnesium. Magnesium tin alloy is a recently developed Roche magnesium alloy. The alloy usually contains nearly equal amounts of tin, amount of over 4 weight percent. This is much different from typical magnesium alloys. For the processing route, the alloy is expected to be deformed in the solid solution state, then subjected to aging treatment to obtain better mechanical properties. Though different precipitates have been found in aged alloy and the corresponding mechanical properties has been characterized. The multi-phase microstructure of the alloy containing different precipitates. They can be beneficial in terms of strengthening but will also significantly affect the corrosion properties. This is Figure 2. Figure 2 shows isothermal aging curves at 200 degrees Celsius for the binary magnesium 1.3 tin alloy, the two ternary alloys with additions of 0.4 and 1.2 zinc, and the quaternary alloy with zinc and sodium additions. Since the very negative corrosion potential of alpha magnesium, the corrosion of the aged magnesium alloys, it may be accelerated by the microgalvanic coupling between anodic alpha magnesium phase and the precipitates. It also has been reported that the proper morphology and distribution of the precipitates may also act as barriers against corrosion propagation. It is still unclear the effects of aging treatment on the corrosion resistance of magnesium, tin, zinc, aluminum alloys. The aim of the study is to elucidate the relationship between the age hardening response as well as the corrosion properties. The results can advance our knowledge on the strengthening and corrosion mechanism of TZA442 alloy in terms of precipitate microstructures. This is Figure 3. Figure 3 illustrates PEM micrograph of the peak age microstructure of the magnesium 1.3 tin alloy in the magnesium and the beam directions. The respective microbeam diffraction patterns from the precipitates are shown in B and D, together with an interpretation of the patterns in C and F, from which the precipitates are identified as magnesium 2 tin. An enhanced age handling response in magnesium tin based alloys containing zinc. Additions of zinc and zinc plus sodium to an age hardenable magnesium 1.3 tin alloy have been examined using hardness measurements and transmission electron microscopy. Zinc addition resulted in a substantial. It increases for 300% in hardening increment after aging at 200 degrees Celsius, but the time to peak hardness was relatively unaffected. Combined additions of zinc and sodium show features typical of separate additions of sodium and zinc, which is a large increase in the observed hardening increment, an acceleration of the time to peak hardness, and a change in particle morphology. Furthermore, the combined zinc plus sodium additions resulted in synergistic effect on precipitate stability during overaging and the time to peak hardness. The stability of magnesium-2-tin precipitate formed in the magnesium, tin, zinc, sodium alloy was much greater than those usually observed in the magnesium, tin, sodium system, and the time to peak hardness was much reduced from 58 hours in the magnesium, tin, sodium alloy to 7 hours in the magnesium, tin, zinc, sodium alloy. Magnesium tin alloys for orthopedic applications. As extruded magnesium tin alloy with various tin content were fabricated. Microstructure of alloys vary with increasing tin content. Mechanical properties of alloys could be adjusted by controlling the tin content. Corrosion properties of alloy could be adjusted by controlling the tin content. As extruded magnesium-1 tin and magnesium-3 tin alloys did not induce toxicity to cells. Materials and methods for orthopedic applications. Magnesium tin alloy ingots with nominal composition of 1, 3, 5, and 7 weight percent tin were prepared by melting pure magnesium for 99.98 weight percent, pure tin for 99.9 weight percent in the middle frequency induction furnace, and quenching the stainless steel crucible with the melt in salt water. The melting process was carried out in a mixed gas atmosphere of sulfur hexafluoride and carbon dioxide to prevent the melt from oxidation. The ingots were heat treated at 520 degrees Celsius for 24 hours, followed by quenching in water at room temperature. Finally, the heat-treated ingots were preheated at 300 degrees Celsius for 1 hour and extruded into cylindrical rods at that temperature with an extrusion ratio of 25:1. The extruded magnesium tin alloys were denoted as magnesium-1 tin, magnesium-3 tin, magnesium-5 tin, and magnesium-7 tin respectively, according to their nominal chemical compositions. These samples, which are 10 times 10 times 2 millimeters cubed, were cut from cylindrical rods for microstructure characterization, immersion tests, and cytotoxicity tests. All samples were ground with silicon carbon paper up to 1000 degrees, ultrasonically clean and dry. This is figure 4. It illustrates surface morphologies of as-extruded magnesium tin alloys after immersion in Hang's solution for 500 hours. A shows magnesium-1 tin, B shows magnesium-3 tin, C shows magnesium-5 tin, D shows magnesium-7 tin, and E shows EDS analysis corresponding to SI A area. The inserted photos were in a large view of local area.
Last but not least, the conclusion. This finding is interesting for development new magnesium standard-based alloys in the future, with further appropriate alloying and processing to control both size and distribution of the second intermetallic phase. The following conclusions are drawn from the present investigation. With the increase in aging time, the strength properties are increasing drastically. On the other hand, the ductility property decreases. The corresponding grain size is also decreasing with the increase in aging time. The grain connectivity, grain boundary triple point density, is also an important parameter which determines the strength of an alloy, which is also showing increasing trends as with the aging time and their corresponding strength properties. On the other hand, opposite trend is found with the ductility parameters. The area fraction of eutectic primary alpha magnesium plus eutectic alpha magnesium Mg2 stannum is also increasing with the aging time, which influences the mechanical properties. Thank you.